This paper, authored by Christopher Young, introduces a novel approach for measuring gravitational field strengths on exoplanets and other celestial bodies. The method, termed the pan-gravity framework, aims to provide accurate and efficient gravitational calculations by relying on directly observable parameters rather than traditional mass-based assumptions. This represents a significant shift in gravitational modeling, with potential applications across planetary science and astrophysics. Gravitational field measurements have long been central to understanding planetary formation, stellar evolution, and cosmic dynamics. Classical gravity models, grounded in Newtonian mechanics and later refined by Einstein's general relativity, typically depend on assumptions about mass distribution. However, these assumptions can be uncertain and computationally intensive, especially for complex systems like exoplanets, neutron stars, or black holes. The pan-gravity method removes this dependency by deriving gravitational acceleration from geometric, orbital, and energy density parameters, specifically utilizing observed rotational velocities and planetary radii. This energy density-based framework offers computational efficiency and avoids circular dependencies on mass estimates, which is particularly advantageous for exoplanets where direct mass measurements are often unavailable. The foundation of this method rests on the stress-energy tensor from general relativity, which encapsulates energy, momentum, and stress distributions in spacetime. Traditionally, the time-time component of this tensor represents energy density and influences spacetime curvature. Unlike conventional approaches that prioritize static mass as gravity's source, the pan-gravity framework emphasizes energy density tied to rotational and orbital dynamics. This allows for a more comprehensive model that integrates motion, geometry, and gravitational interactions, aligning with relativistic principles and capturing effects like mass-energy equivalence and anisotropic stress. A key element of the method is the gravitational energy density function, denoted as UG, which arises from energy redistribution within spacetime caused by gravitational fields. This function is derived from the stress-energy tensor components but focuses on non-mass contributions such as pressure and shear stress. The formulation includes correction factors that account for geometric scaling and energy redistribution effects, one adjusting for the nonlinear relationship between volume and surface area interactions with an exponent of approximately 2.1, and another correcting for elasticity-driven energy redistribution with fractional scaling exponents. These factors ensure that energy redistribution in non-uniform spacetime is accurately represented, reflecting how gravitational fields are sensitive to surface effects and anisotropic energy flux. To incorporate higher-order effects, especially relevant in strong gravitational fields, the method extends Einstein's field equations by adding terms that capture spatial stress gradients and tidal interactions. These include corrections from the Weil tensor, which accounts for long-range curvature distortions not directly sourced by local energy density. The framework introduces a tidal stress-energy tensor that models spacetime elasticity responses to variations in gravitational gradients, ensuring self-consistency under dynamic conditions such as rapidly rotating systems or binary mergers. Spacetime elasticity, or its capacity to dynamically respond to gravitational and rotational forces, plays a central role in this method. Rotational energy flux contributes to spacetime curvature through frame dragging effects, where spacetime itself is twisted by the rotation of massive bodies. The pan-gravity framework incorporates these effects by modifying the stress-energy tensor and Einstein's field equations to include rotational energy terms. This leads to a reformulation of the Kerr metric, which describes rotating masses in general relativity, replacing mass-dependent terms with effective energy contributions derived from the stress-energy tensor. This ensures that rotational effects emerge naturally from energy flow without relying on mass as the primary source. The core equations of the framework quantify spacetime elasticity as a function of orbital velocity, rotational period, geometric properties such as surface area and volume, and a correction factor that combines area and volume dependencies. Correction factors adjust for deviations from perfect spherical symmetry, ensuring accuracy regardless of the celestial body's specific shape or mass distribution. The gravitational energy density is then computed by combining elasticity with these geometric corrections. Finally, gravitational acceleration is expressed as a function of energy density, system volume, radial distance, and fundamental constants, the gravitational constant and the speed of light, thereby eliminating mass from the fundamental input. Applying the pan-gravity method involves gathering initial observations, orbital velocity, rotational period, and radius. When rotational data is unavailable, a standardized rotational period of 15 hours is used as a reliable approximation. Surface area and volume are calculated assuming spherical symmetry, but corrected using the aforementioned factors. Spacetime elasticity is then computed, followed by the application of correction factors to determine energy density. Gravitational acceleration is derived from these values, yielding a mass-independent measure of gravitational field strength. The framework was tested on various celestial bodies, including Pluto, neutron stars, and planets within our solar system. For Pluto, the calculated surface gravitational acceleration was 0.62 meters per second squared, matching NASA's reported value exactly. For a canonical neutron star with a radius of 12 kilometers, the method produced a surface gravity on the order of 2 times 10^12 meters per second squared, consistent with established relativistic models. Additional calculations for planets such as Venus, Mercury, Uranus, and Earth similarly yielded gravitational acceleration values closely aligned with known measurements, demonstrating the method's robustness and accuracy. In terms of applications, the pan-gravity framework excels in modeling gravitational fields in extreme astrophysical environments where traditional mass-based models struggle. For neutron stars and black holes, where density gradients and anisotropic energy distributions are significant, this energy density approach provides a more precise description of surface gravity, space-time elasticity, and frame dragging effects. In exoplanetary science, the inclusion of geometric correction factors allows for accurate gravitational modeling of irregularly shaped or tidally distorted planets, overcoming limitations of mass-dependent models that assume near-spherical symmetry. The framework's primary advantages are its simplicity and efficiency. By relying on just 3 observable parameters, radius, orbital velocity, and rotational period, it reduces computational complexity and observational demands. This is particularly beneficial for systems where mass determination is challenging or uncertain, such as distant exoplanets or compact stellar remnants. The energy density-based model maintains consistency and accuracy even in irregular or high-energy astrophysical contexts. However, certain limitations exist. The method assumes relatively stable orbital and rotational states, which may not fully capture the dynamics of highly variable or chaotic systems, such as merging neutron stars, rapidly evolving exoplanetary atmospheres, or gravitational wave-dominated binaries. Extending applicability to these non-equilibrium systems will require further refinement. When compared to traditional gravitational models, the pan-gravity framework offers a distinctive alternative. Newtonian gravity expresses acceleration as proportional to mass over the square of distance, effective in weak field conditions, but inadequate for strong fields and relativistic effects. General relativity incorporates curvature of spacetime and stress-energy interactions, but demands complex mass estimations and computational resources. Exoplanet mass estimation techniques, like radial velocity and transit photometry, rely on indirect and often uncertain measurements. Alternative gravity theories, including modified Newtonian dynamics and tensor vector scalar gravity, introduce modifications to fundamental laws to explain anomalies, but come with additional parameters and limited testability. In contrast, pan-gravity aligns with known gravitational acceleration values without requiring mass input. It derives gravity from energy density, spacetime elasticity, and geometric scaling factors, simplifying calculations while maintaining empirical accuracy. Unlike alternative gravity models, it does not modify fundamental gravitational laws, but reinterprets gravitational field strength as an emergent property of structured energy flows and spacetime interactions. Case studies reinforce this alignment. The framework's gravitational acceleration predictions for Pluto, Earth, neutron stars, and exoplanets closely match values from mass-based methods, with deviations typically under a few %. This confirms its reliability and potential as a practical tool for diverse astrophysical investigations. The implications of this work extend to gravitational modeling in multibody systems, black hole accretion disks, and gravitational wave physics, where energy flux dominates field interactions. Integrating pangravity into broader theoretical constructs, such as the Unified Galactic Energy Flow Framework, could provide new insights into cosmic dynamics at both galactic and quantum scales. In conclusion, the pangravity framework introduces a transformative perspective on gravitational field measurement, shifting from mass-based assumptions to an energy density-driven approach. By utilizing directly observable parameters and incorporating space-time elasticity and geometric corrections, it achieves accurate gravitational acceleration calculations with reduced complexity. The method's successful application across a range of celestial bodies, from planets to neutron stars and black holes, validates its theoretical foundations and practical utility. This approach not only enhances computational efficiency, but also offers a reconceptualization of gravity as an emergent phenomenon of energy distribution and space-time interactions. As research continues to expand its applications and address current limitations, pangravity holds promise for advancing our understanding of gravitational phenomena throughout the universe.